So good afternoon, everybody. The ABC of galaxy evolution. So what we're going to be talking about this afternoon is the three factors that you need to know about if you want to understand how galaxies form and how they grow. So when we look at galaxies, beautiful images taken by various telescopes across the world or up in orbit, the Hubble Space Telescope, we see some amazing structures out there. Some solitary galaxies, some galaxies that appear to be interacting with each other, producing weird and wonderful shapes, some face-on spiral galaxies, and some galaxies that have a very interesting structure to them. But the question is, can we understand some of the diversity of the galaxy structures that we see when we look out into the observable universe? So we're going to be thinking about the ABC. The A stands for accretion. In other words, galaxies are formed by matter accreting, matter that was generated or created in the Big Bang. That matter has been accreting under the influence of gravity and forming the early galaxies. The B stands for black holes. Black holes are at the centre of, we think, perhaps all galaxies, or at least the majority of galaxies, seem to have a supermassive black hole at their centres. Some of those black holes are taking in matter from their surroundings, they're feeding on the surrounding gas and perhaps stars as well. And some of those black holes are not feeding, there's no matter falling into them, such as the black hole at the centre of our galaxy appears not to have any matter falling into it, which is good news for us, as we'll see later. And finally, the C stands for collisions. In other words, galaxies grow by colliding with other galaxies. They collide and they merge, and generally speaking, grow in size. So accretion and black holes at the centre and collisions are the ABC of galaxy evolution that we're going to be talking about. So where does the story start? Well, like any good story, it starts at the beginning. In this case, the beginning of everything. Okay, a different talk, but the universe came into existence. It took about 3 minutes to make a universe, and at that point we had everything we needed to make everything that we see now. The universe started as, well, it started as a bang, if you like to think of it that way, and the observable universe, everything that we now see inside the observable universe, used to be no bigger than a few centimetres or so. I like to think of it as a golf ball. And just like a golf ball, it had dimples, meaning that it wasn't strictly speaking dimples, but that's just an analogue to make us understand the fact that the universe wasn't totally uniform. It had variations in density, even at the very early stages of its development. And we can see that variation because ultimately those dimples, when the universe has expanded to a much larger size, eventually we get to see the cosmic microwave background, and again we see those dimples, we see those irregularities because those dimples have imprinted in the cosmic microwave background this variation. Some parts of the sky are a little bit hotter, some parts of the sky are a little bit colder when we look at the microwave background. The microwave background is effectively the afterglow, if you like, of the Big Bang, the light that was released some time after the Big Bang itself. But if we have a universe which is relatively compact and has a little bit of variation of density and temperature in it, how did we get from that ball of very hot particles, how do we get from that to what we see in the observable universe? The observable universe looks empty apart from the fact it's peppered chock full of trillions of galaxies. Some of them look a little bit bluish and look to have spiral arms. Some of them are a little bit redder and appear to have less structure. But how can we understand all of that from starting with a relatively uniform glob of matter from the early universe? Well, you could argue that we can only really understand that through computer simulations. We can get an idea of what might have happened by just thinking about it, but really our understanding of how we go from the early universe being created to a universe full of galaxies, really we need to throw that problem at a computer and number crunch our way out of the problem. In other words, if we start with a whole load of matter and throw in some gravity, how does that actually form? How does it evolve? How does it change? There are lots of simulations available over the last few years. They were sort of unknown many decades ago because we simply did not have the computing power to give us any sensible sort of results. But in the last few decades, there have been lots of computer simulations that attempt to answer the question, how do the stars form and how do the galaxies form out of the soup of particles of the Big Bang? I'm not going to cover all of these simulations. I'm just going to pick one group of simulations. I've picked the illustrious simulations, that's the name they go by, because that tells the story very nicely as far as I'm concerned. So let's just think about what happened in the very early part of the universe. The region of space that we now call the observable universe used to be very small, about the size of a golf ball, and those dimples in the golf ball eventually gave rise to the stippling in the microwave background, but of interest to us is how did that then form into galaxies? Well, basically, if we take a uniform spread of matter with small variations in density, we then say, let gravity do its stuff and see what happens. We can't take the entire universe, but we can simulate what would happen if we take a small volume of the universe, a small cube. I say small, it might be hundreds of millions of light years along one edge, but if we take a cube full of matter that's not quite the same density everywhere, if we put in just little variations and then allow gravity to do its stuff, what do we see? Well, one of these first simulations tells us what we see. That uniform region starts to collapse into what we might think of as a cosmic web. It collapses into filaments and voids. What started off fairly uniform, gravity will concentrate the matter, and we can see this concentration where these filaments meet. We get these little knots where matter is starting to accumulate or accrete. Matter flows down these filaments and forms these blobs, which here are shown as white. White is high density, blue or dark blue are low density regions. Let's just watch that happen again. We start from something fairly uniform, and then over perhaps a few billion years, we see the density increasing in certain regions and decreasing in other regions because of the variations that existed very early on in the universe. And we can see the density increasing as matter flows into these little knots where the filaments join each other. So the densest parts of the filaments, that's where the matter is flowing. The matter is effectively flowing through the filaments and collecting in these knots, which ultimately become dense enough to form stars and galaxies. So that's where the proto-galaxies are born, if you like. But along the way, we can't simply say, let's start with a universe that's full of an awful lot of hydrogen and let's let gravity do its stuff, because that doesn't give us the full picture. We have to build in a certain amount of sophistication. It's not just take a lot of hydrogen and let gravity do its stuff. We have to take into account the fact that as the matter is falling and accreting, stars are being born as well. And when stars are born, we end up with black holes and we end up with supernova. And this is relevant because both black holes and supernova can produce outflows of gas, which will stop some of this matter falling in to make the galaxies. So although gravity is trying to pull everything together, once we start actually generating some stars, and once stars start switching on, that can actually affect the way that matter is making more stars and making the galaxies. So these simulations have to be quite sophisticated. It's not just hydrogen plus gravity and let it loose. You have to know something about how stars are born, how they live, how they die, and how the death of a star like a supernova will produce an outflowing of gas which can affect the way galaxies form. Ultimately, we would like to be able to explain why we see so many types of galaxies. If we take, what is this, 100 or so different types of galaxy that we see in the observable universe, we can put them on this chessboard with the bluish ones on the left. They tend to be the disk-like galaxies, which have often a spiral structure. And we can put the reddish ones over on the right hand side. These tend to be more elliptically shaped and not have spiral arms and not seemingly have much structure at all. So can we explain this diversity of galaxies that we see in the observable universe? Can we actually extract that from our simulations? If the simulations don't give galaxies that look like the ones in our universe, then we haven't done a very good job of simulating how our universe came to look the way it is. So let's have a think of the first step of the A, B and C. Let's have a think about the way matter accretes into galaxies. And before we actually have a look at the result of a simulation, let me just say a few words about the simulation itself. So the Illustris project, one of many, remember, the Illustris project is a set of simulations of galaxy formation that run from essentially just after the Big Bang right up to the present day, because ultimately we're trying to explain why the universe looks the way it does at the moment. And along the way, that simulation has to take into account lots of different things. It has to account for the fact that a lot of the matter in the universe is actually dark matter. I said something about that before, of course. So there's a lot of dark matter in the universe, probably more dark matter than there is ordinary matter. And we have to take into account the astrophysics of stars being born, stars dying, black holes being created, and only then will we be able to get an idea of how matter accumulates and accretes into galaxies. The simulations themselves, the first set of simulations of the Illustris simulation package, they ran for about 20 million CPU hours. A CPU is just a central processing unit, effectively a computer. So it's like having 20 million computers at your disposal, or a few thousand computers running for many, many thousands of hours over the period of 2013 to 2015. After running a number of simulations, it was realized that they could make those simulations a little more realistic by including lots of these stellar astrophysics, stellar formation processes. So what do you call Illustris version 2? Well, you could call it simply version 2, but the people who made these simulations had a little more imagination, and they decided to call the second set of simulations Illustris, the next generation. So it was called Illustris TNG, an obvious reference for those Star Trek fans in the audience. And what I will now call simply the TNG simulations. The TNG simulations ran for something like 200 million CPU hours, and you can see that they completed a couple of years ago or so. They ran on a Cray supercomputer because, of course, if you try running these sorts of codes on a simple computer, if you run it on an average desktop computer, these simulations would have to run for perhaps 10 to 20,000 years for the simulations to give meaningful output. So you really do need these supercomputers that are capable of many trillions of calculations a second in order to get meaningful output of these simulations. The simulations were calculated on various spatial scales. They were calculated on the scales of 300 million parsecs, we'll come back to parsecs in just a second, 100 million parsecs and 50 million parsecs. So a parsec is about 3 light years, so the scales on which these calculations were done were roughly 150, 300 and 1000 million light years. The largest one, as you can see on the pane on the right, the 300 megaparsec, these were carried out to give us the large-scale indication of what the cosmic web looks like. We get a number of filaments, a number of voids, which appear to be lower density regions, and on these scales of hundreds of millions of parsecs, we can get a good idea of what the web looks like. But if we want to look at individual galaxies and how they form, we would have to zoom in to some of these high density regions, and that's what TNG 50 is for. Looking on a smaller scale of 50 megaparsecs or so, that gives us a much better idea of how individual galaxies and clusters of galaxies form. And the intermediate scale of 100 megaparsecs was carried out to make sure that we had linkage between the smallest detailed scales and the largest web filament scales. So just a reminder about light years and parsecs. 1 parsec is defined as 3 and a bit light years. And of course, as amateur astronomers, we tend to prefer, generally speaking, light years. How far does light travel in a year? That's something that we can get a handle on. We know that stars are typically a few light years apart, so that's a good handle. But astrophysicists tend to prefer using parsecs. And if we think of, for instance, the dimension of a galaxy, if we take our Milky Way galaxy as typical, then the Milky Way diameter is about 150 or so thousand light years, and so that equates to about 50,000 or 50 kiloparsecs. And if we think about the distance between galaxies, if we take the distance from the Milky Way to the Andromeda galaxy, that distance is about 2.5 million light years, so that's a little bit less than 1 million or 1 megaparsec. So if nothing else, just remember that light years is typically, a few light years is the distance between stars, and the distance between galaxies is typically of order a few megaparsecs. So that's the only real reason you need to remember megaparsec. It's the typical distance between galaxies. That's all we need as far as that is concerned. So let's have a look at one of the TNG simulations. This is a simulation looking in more detail at how a galaxy is formed. So we're looking at the intersection, if you like, of a number of different filaments that are feeding matter under gravity falling into this region. So let's have a look at a video showing how that progresses over a few billion years. You can see matter is coming in from all directions, and it's a rather chaotic mess to start with. Gas is going all over the place. This could represent gas, it could represent dark matter, but the material is moving all over the place, and we can see structures starting to form as time goes by. Just like an ice skater who pulls their arms in and spins faster, so matter falling into this region is spinning faster and faster, and as time goes by we can start to see the structure of something that looks akin to a spiral galaxy. Let's just run that again so we can watch the process over a few billion years. To start with, it looks rather chaotic. A lot of material is still falling from outside. Some of it simply crashes into the material that's already in that region, and we can start to see rotation building up. Occasionally we can see a little clump which looks like it might have been a galaxy in its own right, but eventually that gets swallowed up as all of this matter accretes into this particular lump of this particular galaxy we're looking at. So a lot of the gas, a lot of the hydrogen that's flowing into this region is being used up. You notice that it's looking quite yellow in the middle. This is simply a color coding, meaning yellow is relatively dense, and you can see the outer parts of this particular frame are now quite dark, indicating that a lot of the matter has now been depleted from these outer regions and has flowed into this central region, forming this prototype galaxy. We can ask ourselves whether or not the simulations produce anything like realistic galaxies. So in the background here we have an inverted image, black on white rather than white on black, showing us the filamentary structure of the cosmic web. And if we look in a little more detail at where we have knots indicating high density, we can see certain structures that we recognize as galaxies. But we can ask ourselves the question, are the galaxies that are generated in this simulation, do they look the same as real galaxies? Do they look anything like the galaxies that we would see if we look out into the observable universe? Well, here we have a few examples, and we can tie them up by saying, well, if we look at observations, we can find galaxies that look a little bit like the one in the top panel there. We can find another pair of colliding galaxies that looks a little bit like the one we see in the second panel, and again we can see other galaxies in this case that looks very similar to the one in the bottom there. So yes, whenever we get a simulated galaxy, it normally looks realistic in the sense that we can normally see something in the sky that bears a passing resemblance to those galaxies. So it looks like we're on the right track. The simulation seems to be producing realistic looking galaxies. But if we want to look in detail, then we don't want to look on the scale of 300 megaparsec. That's great for the filamentary structure of the web, but if we want the detail of what's going on in individual galaxies, we would look at TNG 50, the smaller scale of 50 megaparsecs rather than 300 megaparsecs, to look at the detailed structure of individual galaxies. And if we do that, we find that here we've got, 25 or so galaxies. On the left, they're shown with a color coding that shows you where is most of the hydrogen in these particular galaxies that are forming. In other words, where does the gas end up when it's been accreted into this little collection? And so the yellow is where the hydrogen is densest, and the purple is where the hydrogen is less dense. And on the right-hand side, there's those same galaxies again, but this time saying, well, if that hydrogen makes stars in the way that we think we understand it does, where would those stars be, and how brightly would those stars shine? In other words, what would those galaxies actually look like in visible light, rather than where is the hydrogen gas? What would those galaxies look like if we were able to observe these so-called simulated galaxies? And there's the galaxies on the right-hand side. And if you look at the various structures, and some of them have very loose spiral arms, some of them have quite tight spiral arms, it's not unreasonable to look at that. And if you think about, for instance, the Messier catalogue, you can see that, yes, those do bear a good resemblance to a lot of the galaxies that we see out there. Not only the galaxies that are quite close to us, but some of the more distant galaxies as well. And as well as producing galaxies of a spiral structure as well as other structures, we can ask what sort of mass of galaxies are produced, and in particular, is it possible in these simulations to simulate the formation of a galaxy similar to the Milky Way? And indeed, the TNG 50 simulation does indeed generate a number of different galaxies with masses of somewhere around 200 billion stars, 200 solar masses, which is approximately the mass of the Milky Way, and indeed they look very much like the Milky Way. This one on the right, for instance, if we look at it face on, we see a number of spiral arms, just like we assume that the Milky Way does. And if we look at it edge on, you see that it's relatively flat, it's a pancake with a little bit of a bulge in the centre. So yes, the sort of structures of galaxies that are generated in these simulations do indeed look like the galaxies we can see in the distance, and some of them do indeed look like the Milky Way. So it looks like these people who have generated these simulations are indeed getting the physics right. Let's have a think about what's going on in the middle of a galaxy, where a number of galaxies, perhaps all of them or a very large fraction of them, seem to have a black hole in the centre. So how do we know what lies at the centre of the galaxy? Well, we can have a close look at the stars orbiting near the centre of the Milky Way. Our Sun takes over 200 million years to go around one loop, one orbit, if you like, of the Milky Way, but stars much closer to the centre seem to be orbiting something, seem to be going around something very massive. There are lots of stars that are moving in orbit around something we cannot see. Something that must be very massive to keep those stars in their orbits, but relatively compact, and we think that is a black hole. So for quite a few years, for over a decade, the orbits of stars very close to the centre of the galaxy have been monitored, and a number of stars are moving in elliptical orbits, which tell us what the mass of that central object must be. It must be large enough to keep those stars moving in orbits, and some of these orbits have a period of maybe only a few years, so it must be a very massive object to make those stars move the way they do. And it's been calculated that not only is it very massive, it must also be very small. It can't be a huge object, otherwise of course those stars would collide with each other. It must be a very compact object, that little black dot right at the centre of this particular chart. So it's been calculated that the object must have a mass of approximately 4 million solar masses. That symbol there, M circle dot, is just shorthand for the mass of our Sun. Not that there's anything special about the mass of our Sun, it's just a convenient unit to use. So this object has a mass of about 4 million solar masses, and it must be very compact. It must be no more than, let's say for the sake of argument, the orbit of Pluto. Our solar system is shown in the bottom right of that panel just for scale. So a size of no more than a few light hours or so, the size of the solar system, but it has a mass of some 4 million solar masses. And so we deduce that that must be a supermassive black hole. So that's just a way of saying that. There's our Milky Way. This is of course seen from the inside rather than seen from the outside, but our Milky Way galaxy has got a supermassive black hole as determined by the orbits of the stars of a mass of 4 million solar masses. Other galaxies have black holes. It's a little more difficult sometimes to measure what those stars are doing, so we can't determine the mass of a central black hole for every galaxy that's out there, but there are certainly quite a few for which we've measured the mass of the central black hole. For the Centaurus A galaxy, it's been determined that the black hole at the centre of that galaxy has a mass of 100 million solar masses. And that's thought to be responsible for these sort of jets or lobes that are coming out of this particular galaxy. Black holes can feed on matter falling into them. If a star gets too close to a black hole, the star might be ripped apart and the matter then tries to fall into the black hole. All of the matter can't go down the plug hole at the same time, so a lot of the matter ends up in a so-called accretion disk spinning around the black hole, waiting its turn to go into the black hole itself. So when we talk about black holes feeding, we're talking about matter that is falling into the black hole, which is not instantaneous. It can take quite a while. As the accretion disk forms, it gets hot, and that can radiate radiation, it can radiate visible light, radio waves, X-rays, etc. It's actually a very efficient process. Matter falling into a black hole is a very efficient way of turning matter into energy or radiation. You also notice that as well as the accretion disk, there appears to be these jets coming out perpendicular to the accretion disk. And these jets, well, you could argue that we don't really know what those jets are. We think those jets are very energetic particles, and we think they're coming out in these directions, probably because of magnetic fields that are guiding them in those directions. But that's still an ongoing area of research. Here's one galaxy with a jet. It's called M87 in the constellation of Virgo. Perhaps that's a little too small, so let's blow it up with a Hubble Space Telescope picture. We can see the centre of the galaxy in the top left and a very large jet which is coming out of the galaxy, and we think that jet is coming out of the supermassive black hole at the centre of the galaxy. Why does it appear to be just one jet? Most of the physics tells us there ought to be a jet coming out in both directions, back to back as it were, but it just so happens that we are seeing one jet coming towards us, and the jet that's flying away from us, well, that appears not to be very clear or not to be very bright. So we're only seeing the jet that just happens to be coming in our direction. So it just looks like one jet rather than two. But in terms of what do we think is powering that jet, well, the Event Horizon Telescope of a few years back coupled together radio telescopes from around the world to try and get the largest baseline by combining the outputs of these various telescopes, all looking at the same object. They looked at the heart of M87 as well as the heart of a Milky Way galaxy as well, and by looking at the heart of the M87 galaxy using all of these telescopes together, they managed to get this image. It's been determined that the supermassive black hole at the heart of M87 is an absolute monster. It has a mass of 6.5 billion solar masses. Remember, the one at the centre of our Milky Way is only about 4 million, and this is some 1,000 times bigger. What we're effectively looking at is an accretion disk, slightly brighter on one side compared to the other, and there's this shadow in the middle because light is finding it very difficult to get past the black hole. If we think about what it actually looks like, if we were to look at it from above, we simply see the accretion disk as a sort of a pancake. But as seen from the side, it looks rather more distorted. From above or below, it just looks like a disk. But as seen from the side, we might expect it just to look like Saturn's rings, but in fact it looks very distorted, in the sense that if it was just Saturn's rings, we would just see an ellipse from a circle seen edge on. But light from the distant part of the ring is finding it very difficult to go past the black hole. The black hole's gravity is so strong, the light is getting bent, so we're seeing the far side of the accretion disk, both on the top and we're seeing it on the bottom as well. It's a result of the extreme distortion that's immediately around a black hole. So effectively we're seeing the accretion disk with a shadow in the middle there. To give an idea of just how powerful these supermassive black holes are and how they can affect the way galaxies behave, if we look at Hercules A, there's Hercules A in the middle of the image there. It's a visible picture taken by the Hubble Space Telescope. Just next door to it, just below, there seems to be a little spiral galaxy. Conveniently so, if that spiral galaxy was at the same distance as Hercules A, I'm not sure if it is or not, but if we just imagine that it was at the same distance, that would be about the size of the Milky Way. So that little spiral galaxy simply gives us an idea of scale. So you can already see that Hercules A is a large galaxy in its own right. If we simply look at the amount of light it's producing, and if we think about drawing a circle around it that contains all that light, you can see that's huge compared to the Milky Way galaxy itself. But the actual output of the supermassive black hole at the heart of Hercules A is producing jets which are far larger than the galaxy itself. If we image those jets using a radio telescope, here the very large array Socorro in New Mexico, this radio image shows us that the black hole at the center of the galaxy, which we can't actually see, has produced two jets back to back, and these jets are ploughing into the gas that's sitting in between galaxies. We might think of galaxies being separated by essentially nothing, but actually there's still a lot of gas floating around in between galaxies, and these two jets are ploughing into that gas and producing these shock waves, if you like, these lobes, these radio lobes, which you can see are on a vast scale compared to the galaxy itself, and absolutely huge compared to the dimensions of the Milky Way galaxy. And that, remember, is being generated by a supermassive black hole, which is no bigger than the solar system. And you can appreciate how tiny that is on the scale that we're looking at. So if a supermassive black hole is feeding voraciously, in other words, if gas and probably stars are falling into that black hole and generating a large accretion disk, then a lot of energy is being output from this region. And then this particular galaxy with this supermassive black hole at the center would be called an active galactic nucleus, an AGN. In some cases we can see an AGN and we can hardly make out the galaxy because that's so faint compared to the very bright nucleus which is being powered by this supermassive black hole. The most energetic type of AGN is called a quasar, and they emit so much radiation, either in the form of light or possibly X-rays or radio waves. They emit so much radiation they can be observed from absolutely huge distances. And just because I could, I decided to try a lockdown challenge last year and actually tried to image one of these quasars, not using a telescope, but just using my DSLR camera. And so I actually managed to find this particular quasar. This is a very distant object. It's about 25 billion light years away. If we blow it up, it's barely a pixel in this image I've taken from the camera. Even if you were to use a telescope, you still wouldn't see much more than about the same. But the point is that this particular object is producing so much energy, even though it's 25 billion light years away, even though the light from this object has been travelling for most of the age of the universe in order to arrive at the camera, it is still visible. It is still visible in a DSLR camera, even though it's 25 billion light years away, and the universe expansion is carrying it away from us at twice the speed of light. It is still possible to image one of these because there is so much radiation being produced by these galactic centers. If we have a look at how massive is a black hole compared to the galaxy it's sitting in, Strictly speaking, this is not plotted as a function of the galaxy mass, it's the mass of this central bulge of the galaxy. But if we do that for a number of different types of galaxy, we see in the bottom left, there's the Milky Way, a relatively small galaxy, or at least the bulge in the centre is not particularly large in the Milky Way. So it's down there on the bottom left because it's not a particularly large galaxy bulge, and it's not a particularly large black hole, being only a few million solar masses. But if we compare that, for instance, with the one we saw earlier, M87, that is a monster, both in terms of the size of the galaxy and in terms of the size of the black hole, some 6 billion solar masses. So we can see there appears to be a relationship between how big is the galaxy and how big is the black hole at the centre of that galaxy. But to some extent, we don't really understand why. In other words, which formed first? Did matter flow in from the filaments and make a big black hole, and then a galaxy starts to collect around it? Or do we form galaxies and then over time does a black hole start to develop at the centre? Or do they evolve side by side? Again, an ongoing area of research to try and understand the relationship between what a black hole is doing at the centre of the galaxy and what the rest of the galaxy is doing. So let's move on to the final part of our ABC. C is for collisions. So galaxies grow, we know how they form in the first place, but they grow and change through collisions and mergers with other galaxies. So when we look at an image like this on the left-hand side, we can get this false impression that galaxies are rather static. Beautiful structure though it may be, yes, we know that galaxies rotate, but we know that they rotate over, I don't know, hundreds of millions of years typically. And so over a human lifetime, they seem to be essentially static. And it's easy to get fooled into thinking that they don't actually change much, other than if we come back in 100 million years, maybe that galaxy will be upside down because it will have rotated a little bit. But that belies the fact that in fact galaxies have a very checkered history and a very dynamic history in terms of their evolution. We can take snapshots in which it's clear that some galaxies are interacting with each other. Here we see a couple of galaxies, a couple of pairs of galaxies, which appear to be rather distorted because each galaxy is affected by the tidal forces produced from the gravity of the other in the pair. And here we see a beautiful example, this is the rose galaxies, where we seem to have a spiral structure that's been very distorted by the presence of a second galaxy. So we can take snapshots like this and we can tell that galaxy interactions and collisions take place, but we can't fully understand the influence of collisions and mergers unless we run the simulation in a computer and actually look at videos of how the galaxies interact with each other. And then the picture is very different from this static snapshot. We realize that, especially in the early universe, the environment of any given galaxy was extremely chaotic. So we can see here, again on a spatial scale of what is it, a megaparsec or so, we can see hundreds if not thousands of galaxies all buzzing around each other in this galaxy soup. There's a larger galaxy at the top and the bottom starting to come together near the center of the image now. They almost merge with each other, they pass each other, and now they merge with each other over the period of a few 100 million years. And we can see that not only have we just witnessed galaxies merging with each other, notice a few other things. There's a very large galaxy at the center. I'll run this again so you can watch it. A galaxy comes in from the top, a galaxy comes in from the bottom, and then they merge together to make a larger galaxy. But notice that this large galaxy is surrounded by lots of smaller satellite galaxies, it would appear. And notice also that the sky in the background is not black. There is definitely light coming from these regions, which means there's gas in these regions. Remember, there is always some gas in between galaxies, as we saw from the jets produced by Hercules A, for instance. So let's run that simulation again. We see a big galaxy coming in at the top and a big galaxy coming in at the bottom, and they've got lots of satellite galaxies buzzing around them. These sorts of simulations tell us that it is very common for a big galaxy to have a lot of smaller galaxies as satellites. Again, we see these two large galaxies just pass each other and then they merge together. There they pass a second time and finally they merge into one very large galaxy. These sorts of simulations tell us that, well, surely the Milky Way is quite a large galaxy. Shouldn't it have a few hundred satellites? We look out there, and as of a couple of decades ago, we counted all of the satellite galaxies of the Milky Way, and there appear to be about a dozen of them, whereas these simulations say there should be hundreds. So, are the simulations wrong? Are they getting the physics wrong? Well, it turns out no, the simulations actually appear to be correct. The problem is, some of those satellite galaxies are rather fainter than we appreciated. And now that technology has improved and we have imaging devices that can see fainter galaxies, we now realise that the Milky Way is indeed surrounded by not a dozen, but probably a few hundred satellite galaxies, just as these simulations indicate. So here's another way where we're getting a better understanding of why things are the way they are through the use of computer simulations. When we look at clusters, I'm sure a lot of you have seen clusters of galaxies imaged by the Hubble Space Telescope, and they often look like this image on the left. Quite often a large number of fairly reddish, elliptical looking, relatively unstructured galaxies, and perhaps a few blue spiral galaxies as well, as you can see on the left hand side, and perhaps in the background as well. Why should that be? Well, when we're talking about a cluster of galaxies, they're quite crowded. A lot of galaxies are existing in a relatively small amount of space. And if they are crowded, that means collisions are more likely. And generally speaking, when spiral galaxies collide, they tend to lose their spiral arms. They lose their spiral structure, and it tends to homogenize. It tends to reduce the galaxies down to a relatively unstructured elliptical blob. And so these elliptical galaxies are the results of perhaps spiral galaxies, perhaps other galaxies, merging with each other over the past few billion years, producing a predominance of elliptical, slightly redder galaxies. We can see what would happen, for instance, when two particular galaxies collide. If we look at the Milky Way galaxy in the top right, the Andromeda galaxy in the bottom left, it has been calculated that these two galaxies are going to collide with each other about 4 billion years from now. The Triangulum galaxy M33 is in the vicinity but doesn't actually take part in this collision. It's simply a spectator. So let's watch what happens as the Andromeda and the Milky Way, under their influence, their mutual gravitational influence, what happens when they come close to each other. We're now at 3 billion years, they're getting very close. We're now at 3.5 billion years. At 4 billion years, the galaxies pass through each other. The stars probably don't hit each other, but all of the gas of one galaxy interacts with the gas of the other galaxy, and they pass through each other, and then they come back a second time, and then ultimately they merge together and settle down into something which you notice doesn't have any particular spiral structure. It looks like we end up with a fairly amorphous elliptical galaxy once the Milky Way has collided with the Andromeda galaxy. We can think about what that might look like. That's what we see in the sky now. If we're in dark enough skies, we see a band of the Milky Way because, of course, we're looking at the spiral structure from the inside, and there's the Andromeda galaxy over on the left-hand side. We can think about what that would look like in a billion years from now. The Andromeda galaxy will be a little bit closer, but will look pretty much the same. Just a much easier target now for astrophotographers, now that it's a really large object in our night sky. After 3.7 billion years, they still haven't collided yet. The Andromeda galaxy hasn't quite collided with the Milky Way, in the sense that the outer stars are still gravitationally bound to Andromeda, and similarly for the Milky Way. But as soon as we start edging forward from this point, the Andromeda galaxy is going to start disrupting the Milky Way and vice versa. Maybe we won't worry too much about this particular event, because by this point, in 3 to 4 to 5 billion years, our sun will be coming to the end of its lifetime. But if it can just hold off being a red giant for long enough, then we will actually witness something like this. The Andromeda galaxy will start passing through the Milky Way, and there will be a few 100 million years of absolute chaos as they pass through each other and each disrupts the other. There will be, this is now 3.9 billion years into the future, there will be an enormous amount of new star formation, because as soon as you disrupt a galaxy, as soon as you start prodding it, as soon as you start disrupting the clouds of hydrogen, you will catalyze the production of new stars. So there will be a burst of new star formation, as we can see in these pink regions here. At 4 billion years, the two galaxies will have passed through each other, and the Andromeda galaxy now looks very different because its spiral structure has been disrupted by its passage through the Milky Way, and over the next few 100 million years they will eventually settle down, and at some point we will still see the two nuclei of the heart of Andromeda and the heart of the Milky Way, but if we wait just a little bit longer, even those two nuclei, the centres of both galaxies, will merge into one galaxy. What do we call it at that point? Well, we can't really talk about Milky Way and Andromeda because you can't point at any star and say, was that star part of the Milky Way or was that star part of Andromeda? The identity is completely lost. So at that point, we'll need a new name for the galaxy. Milkdromeda? Andrilke? Don't like that. Androway? We've got plenty of time to decide what the name will be. But ultimately, not only will the nuclei of these two galaxies merge with each other into this new elliptical galaxy, but we assume the black holes that are at the centre of the Milky Way and the centre of Andromeda, those two black holes will merge with each other. And it's quite probable that that new supermassive black hole will start feeding on all the gas and all the stars that accidentally got a little bit too close to it. And it's possible that this new galaxy will actually turn into a quasar. So we know that quasars are very luminous and can be seen from enormous distances. What will it be like to have a quasar on our doorstep? Well, maybe by this time the sun will have finished its life and will have turned into a red giant and the Earth will be no more. Maybe we'll have to observe this from a slightly greater distance to appreciate the wonders of the Milky Way Andromeda quasar, if that's indeed what happens. So I've been telling you about the ABC of galaxy evolution. A is for accretion, because galaxies form by the accretion of matter that was created in the Big Bang, the accretion under gravity. The middle of most galaxies have a huge black hole. Some of those black holes are feeding on the surrounding matter and producing huge amounts of radiation. Some of those black holes are quiet, like the one at the centre of the Milky Way, in which no matter is falling into the black hole, and so we don't have an active galactic nucleus in our galaxy. And galaxies grow by the third of the ABC. C is for collisions, and galaxies grow by collisions and mergers of different galaxies over many billions of years. So next time you look at a galaxy either through a telescope or simply look at an image of a galaxy in a book or a magazine, not only can you appreciate the structure of an individual galaxy or possibly the distorted structures of colliding galaxies, but now you know about the ABC and how they came to be. Thank you for your attention.